Here's my 1600 MS-1600 frequency counter on running for a couple of weeks since I ended part 3, and as you see, it's now, this is my shop reference. It was a 1 Hertz high. Well, it's 1 Hertz high now, but it's been holding frequency pretty well within a Hertz. That's a bad cable. I have to throw this cable away. So that's not bad. This is with the TCXO. So now I want to move ahead to the next level of time base. Well, we started with this. We moved up to this. Now I want to move to this. This is at least 2 orders of magnitude better than this. My plan was to use one of these Chinese pre-packaged 10 megahertz OCXOs. They're 5 volts. They've got a 10 megahertz. I think it's a 22 millimeter square oscillator, and the supporting parts. I was going to remove the 10 megahertz oscillator, and I intended to fabricate a daughter board and install this small 8 megahertz OCXO. See, it's on a daughter board with wires going down because it is a different dimension. Just for what it's worth, this one does not fit into a perf board because the pins are not centered like a 1/10 inch spacing, but this one does. However, when I looked at the output from this and the fact that the output frequency didn't seem to vary, I gave up on this idea. Here's that little oscillator turned upside down. And I've connected the power wires, ground, and these are common ground connections, and an oscilloscope to them. This is the control pin, I think. Looking at the oscilloscope, this is ground. So we have a negative going, half volt pulse. So I'm not sure what's happening with this little device. I don't need a negative going pulse. See, it's DC coupled. I could try to invert it with a transistor, maybe get some gain to it, but I'm just not satisfied. I don't think this will be usable for a time base. Now, had this worked, I would have had to put a separate 5 volt supply in the frequency counter, because this draws, well, at least I had to allow for the fact that this would draw some more current, and I didn't want to burden the power supply with that load. Also, I could have wired it so this auxiliary power supply was powered all the time, and that would have allowed the time base to operate continuously, even though I powered down the frequency meter, which means when the meter comes on, the time base is ready to go. But I'm not going to proceed with this. But I would like to go over this oscillator here, which is a very good description of how it OCXO is the auxiliary components are supplied. First thing I'm going to do is power this thing up. And on power up with 5 volts, it draws at half an amp, almost 500 milliamps. In order to prepare for this video, I drew a schematic. Oh, this isn't the schematic, but I drew up a drawing of this board. This is a top view and it's full size, 1:1. There's not too many components on top. However, on the bottom, there's a lot of surface mount components. So I drew it double size. Here's the bill of materials. Here's the schematic and a bottom view of the oscillator. The thing is powered at 5 volts. It goes through a reverse voltage diode, that's good. Some RF rejection circuit. And then power comes down here to pin 5. Pin 5 is VCC. Ground is pin 2. So this 5 volt supply supplies the heater inside the little enclosure, as well as powering the oscillator. The output is taken at pin 1, and there's a series of coils and capacitors here that form a sine wave filter or a low pass filter. The output from this oscillator is a square wave, a pulse. The output here is a sine wave. If I were going to use this as a time base for the counter, I would have gotten rid of this system, or at least C7, and taken the output directly from pin 1, which would have been a pulsed 5 volt. The raw 5 volts passes through this reverse voltage diode, a choke assembly, decoupling capacitor, passes on to this circuit. Now this is a CD431. I've used dozens of TL431s. And what this does is maintain a constant voltage at this point. So if this voltage varies up and down or whatever, the voltage here is very stable. That voltage is applied to a potentiometer, and that goes to pin 3, which is called in the documentation VREF, but I think it's better to call it VAdjust. This is the voltage that fine-tunes the output of the oscillator. So the voltage is, well, it's just as regulated as your power supply is. That voltage is presented to the oscillator. But a regulated voltage, decoupled, is applied to a potentiometer so that we can adjust this voltage and adjust it from a constant voltage source. It's a surface mount. This CD431 is a surface mount device. Here's the pinout. The CD431 has a different pinout than the JC431. If you've got a CD431 data sheet, it probably includes this. Be aware that there need to be different pinout. When I drew this, I used the wrong pinout, and in my mind it didn't work. So that's more for my reference than I guess anybody else's. I should note on this, if you're going to use this schematic, and I've assigned values to capacitors, this is a process of making corrections. Most of the capacitors have no value marking, so I measured them in circuit. And I've indicated that by italicizing. I should have italicized that. So I cover that with a note here. And I do that in the bill of materials. For example, I know it's a ceramic capacitor, but it's not marked, and the value was determined by in-circuit measurement. So the resistors, big capacitors, potentiometer, were all marked, of course. But while I sat here talking to you, the current dropped down to around 250 milliamps. This is the oscillator and my reference oscillator. Now, the little board is a BG7TBL. You see a lot of RF stuff from China. Frequency meters, counters, GPS standards, amplifiers with this BG7TBL logo. Somewhere I've read that this little oscillator is within 0.05 of a hertz when it leaves the factory. And that's probably after like 30 minutes. You can see by the deviation of the speed that it's very, very close. And it's still warming up. And as it warms up, it will slow down. I've adjusted them so they're both on a common 0. And you see the relative motion is not very much. There is another way to display two sine waves and compare them. In fact, you can compare them in phase and frequency. And that's to put the oscilloscope in the XY mode. And so it forms a circle that happens to rotate it around an axis, 45-degree axis. And the shape of the circle tells me that they're both sine waves. And the inclination of the circle tells me the phase. If they were exactly the same frequency, it would form a closed circle, but it wouldn't be rotating around the axis, but it wouldn't be moving. Because they're not exactly the same frequency, the phase is obviously changing all the time. Well, I've sat here for quite a while now. I don't have a wristwatch. I do have a computer, but I didn't note the time. You can see the movement indicating the difference in frequencies. Slowed down drastically. Put it in the XY mode. You see the circle's not revolving or rotating as quickly. So if you wanted to time when these two peaks line up, now, and then say it takes 10 seconds, that would be 1/10 of a hertz difference in frequency. So right now, it's hot. It's not so hot I can't hold my hand on it. but it's noticeably hotter than ambient temperature. And this little board, I showed this on the mail video, cost $20. And it's apparently pretty well calibrated at the Chinese factory. It has a coaxial jack for 5 volts, or it has a pin header, 2 grounds and 2 5 volts.